Mark, nice to have you back. Nice to have you back.
Hello, Dr. M. How are you?
I'm doing well, and straight away, let me introduce you. Standard work. So here we go. Honestly, this time I have to get my first screen first. No, not even this time. There we go. Mark.
Sounds like you don't have standard work there, Dr. M. I don't know.
Hey, Mark, that's what you're going to teach me how to do this on this 35th episode of Dr. M's vodcast.
I don't know. I'm still learning, so don't worry. I've been doing it for 35 years. I'm still learning.
Okay, so the series remains the same, and you're going to do the standard work in two parts. In part one, there's introduction of standard work, 3 elements of standard work. And then we have the part 2 of it, where you talk to us about the cycle time concept and standard work documentation. That's 2 parts.
Yeah, we broke it down that way. Yeah, we broke it down that way to kind of keep the theory, if you will, of separate from the mechanics. So you might want to think about part 2 as being the mechanics, and part 1 more the concepts and the philosophy behind it.
So standard with this part, I will not forget. President and CEO of Lean Horizon Consulting, over 21 years in that field, and prior to that, member of boards of brand, Danaher Corporation. The minute you say Mark Deluzio, Danaher Corporation comes into our mind. And then what follows is that being the first lean accounting process recognized, that you introduced the first lean accounting process in US, one of the units of Danaher's Jake Brake division. University of Hartford, MBA, and there you are, Central Kentucky State University School of Business. There you go. And bachelor's in business and marketing. And this is the most amazing part, which I always love. And this from your Fatland, the book called Fatland. And I read it every time that you have been on Dr. M's podcasts. I'm very proud to have been inducted into SHINGO Academy, the Hall of Fame of Lean. However, I do not let this symptom my growth. After 30 years of practicing Lean, I still consider myself a student. I'm not arrived, nor will I ever. I still have a lot to learn. Thanks a lot for that. And it reinforces in many of us that we also have not arrived, although sometimes our ego takes over us. And this is a reminder to me, since you're a mentor to me, thanks for putting that across to us. So we're going to do this in 2 parts. And part 1, I'm going to stop sharing my screen and hand over to you for the part 1 of standard work. Over to you, Mark.
Okay. I'm going to share my screen. If I could do this right. If you would bear with me for a minute. And are you okay there on the screen, Dr. M? Can you see this?
Perfect.
Okay. All right. Well, let's get going on part 1. Standard work is a very popular subject, and it's probably, Dr. M, as you and I have discussed privately so many times, the most misunderstood part of Lean. And hopefully I can clarify some of the thinking that goes behind it before we get into some of the mechanics. And even with that said, we're not going to get into the mechanics as in-depth as we would when we do an actual hands-on Kaizen event, okay? Because there's a lot more to how to take a time observation and how you work with operators and what have you. Anyway, I'll start with saying this, that Taishi Ono, who was the primary inventor of standard work, him and Sigyo Shingo, Ono believed that without a standard, there can be no Kaizen. And that's sometimes a very confusing concept. However, I like to put it in very simple terms. If you don't have a standard, if it's not documented, what exactly is it that you're changing? Are you changing what's in your mind, which is going to be different than the person standing next to you? Now I got two things I've got to change. And if there's 10 operators, I got 10 different views. And it's all in the ether zone. It's all thought. It's all, I don't know what I'm changing. I have nothing to change. So, and I have nothing to compare myself against when I have a problem and where I deviate, right? So this is a very important concept that Ono-san has brought to us. And it's probably one of the more misunderstood concepts of why you need a standard. And we'll talk more about standards and everything else as we move through. So yeah, you're correct. We're going to do this into two parts. So the first two parts, a little bit of an introduction. And if you can get the introduction right, then I think the rest of it makes a lot more sense to you as you move through. I'm going to talk also about the three components or elements, as we say here, of standard work, which are very important to understand. And then, of course, when we get to part two, we're going to talk about cycle time and the different types of cycle time, because that's a very big ball of confusion as well. And we're also going to talk a little bit about the documentation to show you how we take this concept into actual, memorialized as that one best way as we know it today, albeit it's imperfect. Okay. So that's what we're going to look at today. So I'm going to get into part one, and let's start talking about the introduction. A real quick story. This is Chihiro Nakao, who was one of my principal mentors in life, and he was one of the 10 select people that Ono-san picked into what he called the autonomous study group. Your mentor Imai was one of those guys, Dr. M, as well as Yoshiki Iwata, who was the CEO of Shingijutsu. We were the first ones to bring him over to the United States in 1987. So Art Byrne, George Koenigsegger, as part of that team. You'll hear a guy named Bob Pentland in a minute. And so Nakao was the president, and he became my primary mentor along with Iwata. And he was just unbelievable. Anyway, this whole story here, I'll go through it really quick, but we were at a sushi restaurant one time in the mid-90s somewhere, and I asked him, he talked so much about Ono-san, Taishi Ono, who I never got to meet. My first trip to Japan was in 1990, and he died right around the same time I at my first trip. So I never got to meet Ono. However, they talked about him like he's a god, and they had such respect for Ono-san. And at dinner one night, I said to Nakao, what was Ono-san like? Okay. And Nakao just sat there, and tears started coming down his eyes, down his face. And he got up and he walked away. And I said, okay, what did I do wrong? Well, Shimbo, who was another Shingijutsu consultant, unfortunately, Shimbo's no longer with us. He said to me that nobody ever asked him such a direct question about Ono. And I said, okay, well, I better just shut my big mouth. And so Nakao came back to the table, and after about 3 minutes, he said, would you like to know about Ono-san? And he went on for an hour just telling me stories about Ono. But at the end of this, he said to me, you are a disciple of Ono. You must promise me and commit to me that you'll pass his teachings on, the correct teachings on to future generations. which basically is why I spend so much time on LinkedIn now that I'm kicked off now, but hopefully I'll get back on. Talking about this stuff and correcting people's notions that are just wrong about what Ono brought to the table. Now, that's not to say that what Ono did can't be improved. He'd be the first one to tell you if he were here. But when we just go 180 degrees in a different direction, that's not an improvement. All right. So I committed to Nikau that I would keep people on track as best I could, which is one of the reasons why you and I, Dr. M, are doing this, because you have the same passion as I do in that regard with your mentors that you learn from, Imai and all that. And you want to spread the right word and leave a legacy that, hey, at least we're doing our best to keep this whole concept on track. When I saw him in 2017, I actually flew to Connecticut from Arizona just to have dinner with him. He wanted to see me. He thought I still lived in Connecticut. And at that dinner, he remembered that conversation that we had in 1995 and said that I was the only one at Danaher, from Danaher, that continued and committed to what he asked me to do. He remembered that. Okay. It's not totally true. I was the only one, by the way, but let's not confuse a good story with the facts. Okay. So Nikau was an unbelievable mentor. And to me, quite frankly, the best in the world at what we do. So Nikau says, if you don't understand standard work, you do not understand the Toyota production system. And one of the things that Nikau couldn't understand was how Americans in particular could say they understand things, but couldn't do it. Or have never done it, but say they understand it. That was a concept that was foreign to him. Well, look at where standard work sits on the Toyota production system, the house of Ono, if you will, the TPS house. This is the original interpretation of the first house. Untouched, by the way. So many people like to add all kinds of things into this house, and it's not something to mess with. It's an original document relative to the inputs into this anyway. I have a little bit of artistic interpretation here, but you see that standard work is one of the three things that on the foundation of this house. And on another vodcast that you and I did, Dr. M, we went through this house piece by piece. And so I'm not going to do that today, but we're going to dive deeper into standard work, which is a fundamental core concept. Now, so many people that I know say, hey, we're doing lean. Okay, where's your standard work? Well, it doesn't apply to us. Well, then you're not doing lean. It's like playing golf without a golf club. Okay. A surgeon without a scalpel. I can go on, right? But you're not doing lean if you're not doing standard work. And all the reasons why you don't want to do it are the reasons why you should do it. And we'll talk more about that a little bit later. I want to just start with this slide because this slide was a mentor of mine named Bob Pentland. Bob Pentland, I felt like he was Miyagi and I was, I forget his name now, but, he mentored me when I was in finance. And he's the one that, he and George Konensaker were the ones instrumental in getting me to Japan. And this all led to my going into operations, working with Hino Motors in Japan, part of Toyota, and then eventually was asked to do what we did for Jake Brake, do for Danaher what we did for Jake Brake, and that gave rise to the Danaher business system. Bob Pentland was an incredible mentor. He was a very straightforward, simplistic, and that doesn't mean he wasn't intelligent. He was unbelievably intelligent, but simplistic in how he would lay things out. And this is his slide. Okay. And I will go as far as saying that with all the great people that I worked with at Danaher, if it wasn't for Bob Pentland, I don't believe there ever would be a Danaher business system. Okay. And why do I say that? Because Bob made it happen. George Konensaker was a great visionary in all this, but Bob's the guy that put it into action. And it was because of the success at Jake Brake that George Sherman, our new CEO who came in 1990, said to me, I want you to do for Danaher what you did for Jake Break. And if it wasn't for the success that we had there, it was incredible success in just 2 years, by the way, we never would have done DBS. But Bob starts with standard work, and we'll talk about when do you start with standard work a little bit later, because I think you and I are going to have a question on that. And you go into visual controls. Abnormality detection is what that is all about, visual controls. When you don't actually hit your standard, you look at it on a priority basis and say, well, why? You do root cause problem solving. And then you put your countermeasures in and change your standard. And then the cycle repeats because your standard is the one best way, but your standard is never perfect. And again, along with the concept of continuous improvement, it can always be improved. So as you go through this, you're continuing to monitor, you're continuing to root cause the deviations from your standard work, doing more countermeasures, which could involve Kaizen activity, standard work again, documentation, and all the way through. Now, in the middle, you'll see this thing called CT equals TT. I will explain that a little bit later as we get into this presentation, but that means cycle time equals takt time. Okay, that was a key concept of standard work. And again, when we get into that section of it, Dr. M, I'll clarify this a little bit more. But anyway, the simplicity of this slide is powerful. And I think if anybody would want to just understand what this is all about, here we go. Right. So I think it's important to understand that standard work is not something we did. It's something that we do. Standard work is something that we do on an ongoing basis. It's not a noun, it's a verb. All right. And people say, oh yeah, we did standard work. Well, then if anybody who says to me, oh yeah, we just did standard work, tells me they don't get what standard work is all about. Now, you may have run a Kaizen event and you instituted standard work, but you need to do and work with standard work along the way. Again, going back to this slide, it's not a stagnant thing that you document and stick into a file drawer somewhere or somewhere on your computer. What standard work is all about is using that document for continuous improvement. You're going to have problems. There's absolutely no way you're not going to have issues. And there's absolutely no way that you're not going to be able to, hit your standard 100% of the time, all the time. And that's not, but now you see what Ono said, I've got something to change. When we get to the documentation, you'll see what I'm talking about in part 2. I've got something now I can go back to and improve. Okay. And so that's why this is such an important concept, that it's an ongoing way we do work. It's not something that we do as an event. This is a busy slide, and I don't want to even get into, and I normally wouldn't show a slide like this. So this is more for reference. I'll leave it up here. You can freeze your screen when you're watching this. But there's a lot of misconceptions about what standard work is. And so I thought I'd put, some of the characteristics of what it's about versus what it's not. And one of the things that you're going to hear a lot of people, even in the lean space today, say is, oh yeah, well, it's like engineering IE standards, time and motion study. It is absolutely not a time and motion study as we know it from a traditional industrial engineering perspective. Okay. There are similarities, but it's a totally different concept. For example, we're not looking to optimize a particular operation and make as much as we can on that operation. We're looking to optimize that operation as it relates to our takt time. And we'll get into that again. That may not mean much to the new people listening to this today, but it will hopefully later as we get into this. Okay. So, it's there's a lot of confusion here. That's why I put the slide together. The only other thing I'll say here, by the way, Dr. M, is that standard work are not standard operating procedures. Standard operating procedures are more detailed, all right? And standard work is maybe more at a higher level in terms of the work element. So I may say, this microphone right here, I may say assemble top to body. there may be all kinds of things that have to happen from a standard operating procedure, an SOP procedure, for me to assemble this. Maybe I have to put a glue in here. Maybe I have to add an O-ring, or whatever it is. So SOPs are a lot more detailed, and they get into work instructions, job instructions, and things like that. And by the way, we're not going to talk about this today, but the more visual you can make these and the less verbiage, the better, which is kind of funny because I'm putting a big verbiage slide in front of you guys today, but I'm not walking the talk in that regard. But it's a tool to use to improve the process, not to penalize the operator. 99 times out of 100, if the operator cannot meet the standard, you have a bad process. And the focus needs to be on the process. Now, let me just say this too, while I'm here. If you're running a business and you've got chaotic processes and operators spend a majority of their day firefighting, that is an outright disrespect for people. Okay. And if you expect your operators to always work in chaos, or your office workers, it doesn't matter. And if people are pulling their hair out at the end of every single day, dread coming in on Monday, working excessive overtime, you as a leader are being disrespectful of not giving your people the tools to be able to improve, not giving them the time to do Kaizen, not giving them the time to sort things out, using tools like standard work and other tools within the lean toolbox. You are being absolutely disrespectful and a violation of the RFP philosophy. That's something I just want to point out. So I thought it was always good to use outside examples to compare to what we're doing with lean. So I thought a lot about this, and I thought about, well, geez, an orchestra. Let's just talk about the orchestra for a minute. Who are the people involved in an orchestra over on the right-hand side? Well, it's the musicians, of course, right? What about the process layout? We look at how we lay out the instruments, the percussion's over here, and the brass and the string section's over here. All right, now, once we lay out the orchestra, we need some standard work, right? We need some sheet music. We need some documentation. And everybody's going to have their own roles to play in playing that song. So the sheet music is the score, of course, of the music. And then who's going to keep the beat? That's the conductor. Okay, so all those four elements are exactly applicable to creating a manufacturing cell with standard work, or whether it's an administrative flow. Okay. So what you've got is your production operators, being the people in this case, or an office worker in an admin environment. You've got your flow, your manufacturing cell that's set up. You've got your standard work documentation, which we'll talk about in part 2. And you've got takt time. Takt time, as we're going to talk about in a minute, is the beat. It's a beat, the rhythm. Okay, that all those four things. How many times have we seen people set up manufacturing cells with no documentation, no standard work, no concept of takt time, and all we do is we set up a bunch of equipment. It looks really nice. We take some nice pictures, but we have no concept as to how to execute within that framework of equipment. So it happens all the time. And I will go as far as saying that if you do that and you don't have standard work, you can't even say you're doing lean, despite the posters you put up on the board, despite the what it says in your annual report. It doesn't matter. If you're not doing this, you're not doing lean. Period. No argument after that. So we wouldn't set up an orchestra without a sheet music or a conductor. We shouldn't set up a manufacturing or an administrative flow cell, let's say, without the same. Okay. Standard work is broken down into 3 elements. Now, let's not confuse standard work with all kinds of other standard procedures that we might have. You can have a standard procedure as to how to do a particular journal entry. That's not necessarily standard work. Okay, it might be, that's more job instructions, right? So unfortunately, standard work, the name is such a generic name that it gets confused for so many other things. But I'm here to tell you that if from a pure lean purist perspective, standard work means only one thing to me. If it doesn't have these 3 elements, it's not standard work. Call it something else, but it's not standard work. So the 3 elements are takt time, work sequence, and standard work in process. So the rest of this module, this first part, is going to be to explain those 3 concepts. Takt time, how often a part or service should be produced, and we'll talk about that in a little bit more detail. Work sequence, the sequence assigned to the operator, the manual steps, and standard work in process, that amount of inventory that needs to keep your operators flowing. We'll talk more about that in a minute. So what's takt time? Again, how often a part or service should be produced. So it's the pace of sales in the marketplace. Interesting. That comes right from Toyota. Takt time is the pace of sales in the marketplace, which basically means that the time you have to produce one unit is determined. The time you're allotted, let's say, to produce one unit has to be consistent with your demand. You go back to Bob Pentland's slide, it says the supply equals demand. All right. It's got to be consistent with demand. So you know, in theory anyway, the only way to change takt time is if your volume changes from your customer. That's it. And so we'll get into the calculation in a minute, right? So it's a very important concept. By the way, I write takt time in red out of respect to Ono-san, because Nikao told me a story about how Ono was adamant that takt time needs to be written in red because it's such an important number that they focused on. So I do it out of respect to that, and also it's a good idea to do it because you don't want to confuse takt time with cycle time, as we'll talk about in a minute. Believe it or not, it's a German word. It's not a Japanese word. Everybody thinks it might be a Japanese word. And what it means beat. It means, you know, it means rhythm, beat, right? So that's kind of the pace that you want in an operation. It's interesting because there's something that's an intuitive thing too called takt image, where you walk into a factory and you can own something in really well run factories. You can sense the beat, you can feel it, you can sense it, right? Other factories you walk into, you think you're in a library, and that's the problem, right? So so this is what we want. You know, again, this came out of the German World War II concept. I'll leave it up there. I'm not going to go through every single part of this, but just understand where the origin of takt time came from and why Ono thought it was a good idea to bring it in to the Toyota Motors Corporation. So let's just look at the calculation really briefly. We're going to basically take the available time, and we like to express takt time in seconds. The available time in a shift. So in this case, I'm showing 28,800 seconds, like taking out my breaks, and I end up with 27,000 seconds. If I have to make 350 units, I have a takt time of 77 seconds. That basically means that I cannot have any one operator, we'll talk about work sequence in a minute, have more than 77 seconds worth of work. All right. I can't have a machine that runs longer than takt time, including the load and the unload. All right. So all these things, it's a really key number to assure that you're going to hit the demand that's required. All right. Now, there's other things that could go into the calculation here in terms of meeting times, cleanup time. I didn't show that here, but I wanted to keep this example simple. But I always would say that's got to be standardized too. If you allow 10 minutes of cleanup time at the end of the shift, you would take that out of gross available time. But if that's an excuse for operators to put their coat on early and stand by the time clock, instead of doing their key task to clean up the cell, then quite frankly, I don't allow it. So it's got to be documented and adhered to. So what do we use takt time for? We could use takt time to determine how many operators are required in a particular cell. And that is taking the sum of the cycle time of the operator, which we'll talk about cycle time a little bit later, okay, divided by takt time. So if a product, let's say this mouse that I'm holding in my hand, if you could see it, let's just say this takes, I'm going to make up the numbers, 1,000 seconds to assemble one mouse. In total, from start to finish, 1,000 manual seconds. Forget about machines for a minute. Manual seconds, 1,000. And if my takt time is 100 seconds, according to this first calculation, I need 10 people. It's 100 takt time divided into 1,000. So that basically means that I can't have any one operator in my cell in a one-piece flow environment have more than 100 seconds worth of work. If any one of those operators had 110, let's say, my drop-off rate at the end of the cell is going to be 110 seconds. I won't hit my demand, which means it will force me into overtime, or it will force me to weekends or whatever, right? Or missed shipments. Inventory. This is where we take the lead time of the part divided by the takt time. I'll get more into this a little bit later when we talk about standard work in process. And then we also look at it from a processing capacity perspective. When I look at the machine cycle time and what it takes to load and unload the machine, it's got to be less than takt time. Okay, again, I'll create a bottleneck in that cell if my load, unload, and my machine cycle time is greater than 77 seconds in this example. If it's 90 seconds, that means that, well, everything else being equal, I'm going to get one part off that cell every 90 seconds, and I won't hit my demand. So I got to use takt time and Kaizen that equipment so that we can work within the context of takt time. All right. So those are the three ways we use takt time. Okay. And I've got some things in here about available time. There's a lot of misunderstanding about what you could take out of shift time when calculating takt time. Okay, so I did talk about paid breaks, daily team meetings, cleanup activities, time to do actual problem solving type activities. You may give Friday afternoon off for operators to solve problems, work with engineers and lean people to solve problems. That comes out of the time, right? But you don't take off these things. Fatigue, that's where the time and motion studies come in. Okay. If the operator is getting fatigued because of the process, then one of not two things have to happen. One, that means you have a process that's not robust enough where operators are getting burnt out. Number one, which is disrespect. You want to see that with standard work. You actually want to see that, oh boy, that operator is getting a little bit tired on that one step. Nobody wants to do that particular job because it's ugly, it's dirty, it's labor intensive, right? Well, you've got a bad process. You want to see that with standard work. Secondly, the whole idea of rotating operators within a cell so that everybody learns everybody else's job is a very valuable tool. Because now I've got the ability to move people around, especially when I have, vacations and I have, holidays and things like that, or people are out sick. I now have coverage around the cell. So that helps on the efficiency issue and the fatigue issue too, because you rotate people around, all right? If somebody leaves a cell for an unscheduled break, no, you don't allow that. Doesn't mean you don't let them go to the bathroom, but you don't allow that. This is where a team leader would come in and pick up for that operator while he or she is gone. And then once that operator comes back, so that way the flow of the cell keeps moving. right? And downtime, okay? Quality issues, setup time, setup's an abnormality. So this is where a lot of confusion comes in. A lot of engineers in particular want to document abnormalities into their standard work. And that's not what this is about. We want those abnormalities to stick out like a sore thumb. We don't want you to document and then just say, okay, well, we're okay now because we're hitting our standard. Well, first of all these abnormalities are so chaotic and random that you can't standardize them. Okay. If I said to you, well, on average, we have 4.3 hours of downtime a week, so we need to take that out of our available time. You think it's going to be 4.3 hours next week? No, might be 2, might be 8. Okay. So you can't memorialize and institutionalize abnormalities into your standard. So those things have to come out because I want to see the difference. I want to see, here's the delta without downtime, for example. Here's my line in the sand. I didn't hit it, which means, guess what? I need to do Kaizen to get me back to that standard, right? Go back to Bob Petlin's first chart. That's exactly what that's saying to you. You don't put abnormalities into standard work. Okay, work sequence. This is the path that an operator would take to actually perform one unit. Now, in this example, I show a cell that starts with operation number 1, and it goes all the way around to operation number 11. Some of those operations could be machines, they could be manual steps, assembly steps, could be testing, could be all kinds of different things, right? Doesn't matter. This is the operator work sequence that's assigned to each and every operator. And of course, no one work sequence of any one of those operators could exceed what? Takt time. You've got to be within takt time, because let's just say my takt time is 77 seconds, all right? And let's say operator 2 happens to be at 80. Well, the drop-off rate as I'm standing at the end of the cell after operation 11, if I'm standing there with my hand out, seeing how often a part falls in, and his cycle time's 80, it's going to be 80 seconds, everything else being equal. I'm not going to meet my takt time. I'm not going to meet my demand. All right. So that's why we have to, keep the operators in the context of takt time. Now, think about the operators like a driver on a racetrack with Formula 1, Indy 500, NASCAR. They have to stay on that racetrack as much as possible, which means I don't want these operators to fetch materials and tooling and leave the cell. You don't have the driver of a race car leaving the track to change his own tires or put oil in his car or gasoline or whatever. You want him on that track as much as possible. This is where we incorporate what we call water spiders to bring materials to and from the cell, any kind of supplies, any kind of, whatever the operator needs to perform their task. Now, this is not a seminar on cell design, and maybe we should do one later, Dr. M, on cell design. But you'll notice that this cell goes counterclockwise, starting with number 1. That's because as the operator moves through the operations, typically most people are right-handed. So you're working with your strong side into the operation. In some cells, it's not applicable, it's irrelevant. But in some, where you got the load unload with machinery, most people are right-handed. So that's why you set up kind of clockwise. You're working with your strong side into the equipment. And why is it a U? There's a lot of different reasons. One, from a visual perspective, your materials go in and out at essentially the same point. You have visual management down the cell. It's enhancing communications. Let's say the third operator there had an issue with what operator number 1 was doing at step number 1. If this was a straight line, he'd be so far down the line, he's less inclined to come back to him and say, by the way, you're putting the blue part in, it needs to be red. And I caught the issue, right? So this enhances communication, visual control. The other thing it does is it reduces walk time if you lay your cell out instead of a linear fashion where you have an operator go from, let's say, 7, 8, and 9. You have this operator going back and forth in a cell. The way, let's say, that middle operator is going from 3, 4, 8, and 9, that you're minimizing walk time too. Okay. It's another advantage of a U shape. So that's a whole nother subject, cell design, whole nother subject. There's a lot to cell design. And I would suggest that you and I do a seminar on that one down on
Sure.
the vodcast
Sure.
on the line. Okay.
Sure.
So that's a work sequence that's assigned to each operator. That doesn't mean though that those operators can't rotate. Okay, during the day, during the week, whatever, right? You're going to want that. So we call cycle time of the operator CT with a little O. Okay, cycle time of the operator. And again, here's your NASCAR example, right? Okay, here's your auto race. So I got a water spider that supports the cell. I've got a pit crew that supports the race. And again, the upper right-hand corner there with this with these cars, that racetrack, think about that as the operator's work sequence that they have to do. You know, my example, 350 times during the day to get 350 units out because you're producing at a one-piece flow. All right. And again, as Nikau told us, operators should operate. Drivers in a race car should drive. I mean, it's that simple, right? Okay, the last step here is standard working process. Won't spend a lot of time on this, except for the fact that standard working process is the inventory that allows you as an operator to keep flowing within your work sequence. So for example, on machine number 1 here, I've got a piece of standard working process in this equipment. So when I unload and then load a new part into that equipment and hit the green button, I don't stand there and watch it. I walk away from it while it's machining. Just like you would not stand there and watch your clothes dryer dry your clothes. You'll go and do something else. We don't want operators standing watching machines. And I've heard so many crazy excuses, Dr. M, on this. Well, the operator's there in case there's a problem. Really? So you mean to tell me if a machine crashes or there's an issue, tool breaks, that the operator would have caught that before it happened? And you're going to stand there? And only, by the way, how often does that happen anyway, right? So there's a lot of banal excuses as to why we have an operator stand at a piece of equipment, which is foolish. So we want that operator to move on in the process. So that's what standard working process does. And and this here, hey, here's Toyota Motors definition of standard WIP. Standard in-process stock is the amount of material that is flowing through a process when work is proceeding smoothly. It is the minimum amount of material needed to maintain a smooth flow of production without accumulating inventory. So there will be inventory in your process. And I always have rejected the notion that, lean is about zero inventories. That's like me saying to you, Dr. M, well, take all the blood out of your body, Yeah, you'll lose weight, but guess what? You'll die. And that's what would happen if you take the lifeblood out of your supply chain, your manufacturing process. You do, though, have to realize that inventory is a representation of waste, from the respect that the more you have to have, the more waste you have. For example, if you have a Kanban that has 1,000 parts in it, and you said to yourself, well, I want to cut that in half. Well, geez, I can't cut it in half. Well, why not? Because if I cut it in half, I got long changeover times. I got equipment downtime issues. I got supplier issues. Oh, by the way, those are your next 3 Kaizens. Okay. That's what you're going to work on. A good way to find out what you need to do if you have a Kanban between processes is say, if I cut it in half, what problems are you going to have? Why can't I cut it in half? And once you come up with those answers like I just did, there are your 3 Kaizens. Okay. Go work on them. All right. So that's what this is all about. Okay. And I get kind of detailed here, and I'm not gonna spend a lot of time here, but there is this whole notion of what's called a curtain effect. When a part has to leave the cell and then come back later, you have this in and out thing going on there after step one. All right. So if you look at you start with 50 in the inbox, 0 in the out, and then after the first cycle, it goes to 49 and 1. Eventually, the out box gets filled with 50. That has to go back out to the outside process. A new box comes in on the in, and the process starts over. Okay. So again, I'm not going to spend a lot of time doing this, but we use takt time again, like I indicated earlier, to be able to indicate how much standard whip in that curtain effect do we need, right? So, and again, I don't want the operator leaving the cell to bring those parts over to the outside process. All right.
Mark, I like this definition which you're given on the right-hand bottom, which defines the pitch. Pitch defined as the amount of time the water spider needs to return to the cell in order to keep the operator replenished with the material processed from an outside operation.
Yeah, so if the operator has 50 units in that inbox, and takt time's 2 minutes, that means 100 minutes later he's gonna be emptied. That's how much time the water spreader has to get back to that cell to give him another group of 50 units. All right. If he waits, so what's that? 2 minutes times 50. If he waited instead of 100 minutes, he waited 110 minutes, the operator's going to be standing there for 10 minutes waiting for parts. All right. So that's what we call the pitch. We use takt time to calculate how many units you want there as a pitch. Now, sometimes you don't want to cut it that close, and I will say that I have done this in practice where instead of 50 units, I would put maybe another 5 or 10 units, depending on what they are, just as a little bit of a buffer in case something happened with the water spider or whatever. Just a little bit of a buffer in there. I know that maybe violates the philosophy to some degree, but there is this balance between keeping this thing going and being so pure to the principles that you shut yourself down. All right. So, but that just means though that if I had to do that, I want to recognize that as an abnormality. Okay. My calculation said I need 50. Well, Mark, why are you using 55? Well, because we got this problem, that problem. Oh, good. There you go. Just like taking down your Kanban. Okay. Well, what if you went to 50? What problems would you have to work on not to have that extra inventory? There are your Kaizens. It's the same concept. Okay. But it's important to recognize that, not just do this and bury it as part of your standard. Your standard work should say 50 units. It shouldn't say 55 or 60.
But it's a deliberate decision that has been taken at that point of time, which need to be kaizened and improved, right, sir?
Yeah, and you also have to make it obvious to all that that is not standard. So I would never bake in the 5 or 10 extra units. I'd have them off to the side in a red, not in a red bin, but in a bin that says, not standard, so that you actually have visual management of a non-standard situation. Yeah. Okay. Otherwise, if I bake it in there and say, well, it's 60, I'll never know that there's abnormalities within my process. Okay. Okay, I've got a bunch of rules and guidelines here, which again, not to get into all kinds of crazy stuff here, but we do want to keep it visual, number one. So that I know, Dr. M, as I look at your cell, if I see buildup of inventory between two operators, that essentially means that something's not right in the cell. So a lot of times you can use standard work in process or inventory, if you will, to be your visual cue as to abnormalities. Okay, that's what detecting abnormalities is all about. When you switch over from model A to model B, you don't want to drain your line and then have to fill it up again. You want to be able to have it all there so that you're not having operators wait to fill in all the subsequent processes for the new model. Okay, you want that to be a congruent flow going all the way through. Okay, and that's what the assuring of the flow of the operators is all about. And you don't want to build work in process. So in other words, if I'm an operator and you're the next guy in line and I see you're having problems, I'm not going to continue to build a pile of parts in front of you because you have an issue. We have to go and fix the issue so that we can maintain flow all the way through. Okay. So standard work in process is called standard for a reason. All right. That's why we call it that. And that's the third element of standard work. So basically, just sum this up, Dr. M. I gave you the concepts of the components, if you will, of standard work, but the philosophical issue here is the most important in that without a standard, you can't do improvements. Standard work is not something to memorialize and document all of your random problems, whether they be, machine issues, quality issues, supplier issues, whatever it may be, right? It's not intended for that at all. It's for you to actually document the one best way that you observed, that you observed, and then try to hit that one best way all the time. And when you can't, that is your charter for your next series of Kaizens. Okay. And again, I will go back one more time and say that it is a verb, not a noun. Standard work is not something that we did. Standard work should be something that we do on an everyday basis. Okay. So I'll stop there.
Yep.
And I don't know if you have questions right now or you want to hold those to the next section.
I think you can stop sharing. I just got one situation that you can dwell on Here's a situation, Mark, and want to be very clear. You walk into Gamba. I'm looking at a manufacturing. It can be office or what have you. I'm just giving you an example of a workplace manufacturing. You go there and you're an external, internal. You have just learned standard work from Mark Deluzio. You come over there, and then you see that there is erratic work going on. Operators come. Some operators do it this way. Some operators don't do it, and there's a lot of fluctuation as you stand, watch, and observe. How do you go ahead from there to establish a standard work? There's nothing called a standard work in that place. Nothing. There is. They come, they work, they produce the part, they go. Okay.
You start from scratch. You've never done it before. Okay. First of all, it's very important to bring the operators into the training. Number one, they should be part of the Kaizen team. Number two, and maybe this was a slide that I was remiss on putting into this first part. And you go back to Tashiono. Tashiono says that you should involve the operators in creating the standard. You should not dictate and deploy to them. First of all, they know the job better than anybody. What you have to do, though, is after you train them on the concepts, you have to sit down with them and say, okay, look, show me how to make this part. What are the steps involved in making this part? And by the way, one part, not 10. All right, because you're going to find that they may be working in batch. It may be chaotic. It may be sometimes Charlie does this and Joe does it sometimes. And, they all switch off and they kind of help each other. And when they try to help each other, they're really actually tearing this thing down. So, and not intentionally. Okay. But you get the operators involved and you say, okay, well, now that you've learned the concepts of one piece flow and standard work, I need to have you show me the one best way of, let's say, assembling this part. All right. So the operator starts. And
Can I hold you there?
Look,
this is putting my, this, we're just talking about, we're not talking about a cell, we're just talking about one work, right? So you pick the best operator from there, or you pick any operator from there?
You don't even give that a thought.
Pardon me?
You don't even give that. You don't even give that a thought, because hopefully you're going to be rotating people anyway. See, here's the thing about this whole best operator thing, right? Normally, you're going to find that there's greater variation in operator performance because of the process, not because of the operator, right? And to sit there and judge who's the best operator and who's not. Now, I will say this: I've had situations, Dr. M, where certain operators just did not have the manual dexterity to be good at the job. Okay. And if that's the case, you have to find something else for them to do. It's as simple as that. And I know in a union shop is a little bit tougher, right? Which is why you got to negotiate your contracts in accordance with lean principles, like we did at Jake Break. And so, you know, to say that that operator is better than that operator, there's just certain physical things that some people can't do. Maybe they have really big fingers and big hands and they're assembling small little parts. Well, maybe that's not the job for them. Okay. I mean, I would have loved to play Major League Baseball, and I was good enough to play baseball at the major league level from a defensive perspective, and I had a great arm, but I couldn't hit at that level. So I can't play baseball. Okay. I couldn't play Major League Baseball because I don't have the talent. Well, if you don't have the talent, that's a whole another issue. But I don't like the notion of who's your best operator. I really don't like that notion. And to me, to some degree, it's demeaning.
Yeah, Mark, I understand. I do.
And by the way, when we get into time observations later, I'm going to talk about the fact that you need to have the operator work at a very normal work pace. You don't want them to work like crazy. I've actually told operators, slow down. And they looked at me like I had two heads. Well, I thought you wanted productivity. No, you can't maintain this, and it's not fair to you. I want you to work at a normal, you know, relatively brisk, but a normal work pace. I don't want you to work burnt out. And also, I don't want you to make errors because you're trying to beat the clock. I want you to work at a very normal work pace. All right. And so that's another notion that you have to think about here.
So
right.
Bring you back to standard work. Sorry to have.
No, that's okay. So basically, what when you start this out, there's no stopwatches yet. There's no documentation yet. You're standing there with the operator and say, just show me how you put a part together. Show me that first step of what you do. And they start out, and you just start just writing down the steps. Okay. Now, what's going to happen is when you ask the operator to repeat it again, they may do it differently. Okay. So you have to bring them back and say, look, last time you did step 4, 5, and 6. Now you're doing step 6, 4, and 5. Which is it? And I usually like to have an engineer take a look at this too, because with me when we're doing this, only because the operator might compromise the quality based on the process of manufacturing. So you got to just make sure it's sound from an engineering perspective, but you give the operator some latitude. And what would you prefer? Now, maybe the operator next to that person say, yeah, when I do the job, I do it this way. Okay, guys. So you did understand that we just went through the training and that the whole concept and notion of standardization is very important to us. So could you guys decide then which way you're both going to do this? Okay, we need to have you come back with one way, okay, and put your cards on the table to talk about why you think your way's better, all right, and then decide. Okay, so that's how you do it. You start by, you have to involve the operators. This is not something you do to the operators. They have to almost, in a sense, create the standard work for you, you know, and so you ask them, you know, show me how you do this. All right. And then once we document that, that becomes the standard.
Can I hold you there? Can I hold you there? This process is because there's a little bit of confusion because Sensei Masaki Mai, you know him very well. When he talked about a term called stabilization, when it goes zigzag, and what you said is you are asking that operator to do the thing, and you have an engineer to look at the quality part of it. There's a process involved in that. And then you start documenting it, and that is your standard. But that process is the period of stabilizing, as in making the operator do the sequence of operation, which is comfortable to him and is the right quality, and that you prima facie documented. And the process, would it be appropriate for me to say it's a stabilizing process, but that generates a standard work document. Am I right to that extent?
Yes, you're right. And one of the problems you're going to have is that
I'm saying that the process is of stabilization for a standard. The word stabilization is misunderstood everywhere. That's all what I'm trying to say. That's
yeah, it is, because I know there's people out there I've seen on LinkedIn that says, hey, before you do standard work, you have to fix your machine downtime problems, fix your supplier problems, fix your quality problems, fix this, fix that, create flow. And it's so inconsistent, misunderstood, and illogical to me, because if you really do, so what you're saying is, I'm going to make all these improvements before I put standards in, and Ono's standing there saying, you can't do improvements without a standard. So how could you make all these improvements first and then put standard work in place? No, standard work is the methodology in which those improvements happen. It's kind of like me saying to you, I go to my doctor. Well, you're not my doctor, Dr. M, but you're a doctor. I go to my doctor and I say, well, I'm not going to take your medicine yet until I get better. Well, the medicine is what's going to make me better, supposedly. Okay, so the notion of that everything's got to be improved before I do standard work is an absolute misunderstanding of what this is about. And there are some notable lean people out there who say that, and I am adamant that and by the way, the first thing that we did with the very first series of Kaizens that we did with Shingo Jitsu was standard work. Okay, so we moved equipment simultaneously to create a flow. We did all that stuff. We put visuals in place. That's the other thing about this too. People think that these lean tools stand by themselves, and they don't. The reason they stand by themselves is because consultants love to sell them that way. All right. I cannot talk to you, Dr. M, about doing standard work without cell design, without material presentation, without visual management, without problem solving, root cause 5Y, all these different things. I can't talk to you about doing just standard work without doing everything else. That's kind of going to a golf course and saying, I'm only going to putt today. Well, you got other things you got to do too to play the game.
So when Sensei Masaki Imai says stabilizing point, and the way you are saying it, it is this process that you're following is a stabilizing process. That process is maybe called stabilizing. Yeah. But and at the end of it, you arrive at a standard.
Yeah, and I think stabilization in terms of in my son means that you're stabilizing the process from the respect that you're repeating the same over again. Correct. When other people say stabilize, it's get rid of all my problems, get my machine downtime fixed. So my question would be, why isn't it fixed now?
I love what you said. Yeah. It is that you're testing the repeatability of that. It's repeatability that you're putting into test. Now, once
in that sense, it's stabilized in that sense. Okay,
that's right.
It may not, and it's the one best way that we know today. Okay?
At that point of time.
At that point in time. Although we do know it's an imperfect way to do it.
Perfect.
Right? Okay, because that's a whole
clarifies it. That clarifies it. Now people would understand when Sensei Masaki
we'll see if they do. We'll see if they do.
it doesn't matter. We will improve on
You know,
that.
it's funny, Dr. M. I've had this argument so many times about you got to fix all your problems before you do standard work, right?
No.
I've had this argument all throughout my 30 years, 35 years. And the only thing I'll say to you is that, well, the people who actually invented this, the guys like Imai and Nakao and Iwata and of course Ono and Shingo, and they disagree. So, you know, you can have your view on this all you want. Go fix all your problems first. My question to you is, if it was that easy, why aren't they fixed already? All right. I mean, now you're not doing your job. If you're telling me you've got all these problems, here is a tool that's going to help you with getting to that area of improvement. And you're standing there saying, no, we're going to fix our problems first. Well, then what the heck you been doing all day? What have you been doing up to this point in time? Now we're saying, well, do standard work, and that's going to be the vehicle to make the improvements. No, we got to fix our problems first. Well, you were incapable of doing that up till now. What makes you think tomorrow is going to be any different, or next year? Okay, you're still going to have these problems because you didn't standardize and stabilize, to Imai's point, the process where you can actually visually see where your deltas are, where your differences are.
And that, I like what you said, and what is arrived at is the repeatability at that point of time. And
it's a stabilized way of doing work. You know, I'm going to put this pen together the same way all the time. I'm not going to put it 5 different ways, because if I do it 5 different ways and I want to make an improvement, what am I changing? Especially if it's not documented. It's in your head, it's in my head. I don't know what I'm changing. I don't know.
At that point of time, when you're doing it, you check the best way that has been done, repeated, and just freeze it at that point of time and improve on that later.
Exactly. Yeah, because there's an area there where you're going to have to stabilize and run it, and then notice the deltas. Go back to Bob Hutton's first chart with
yes,
with,
yes.
Then you're going to see, oh, wait a minute, here's my standard that I said I'm going to do all these steps in this order. And guess what? I couldn't do step 13. Why? Because I had this problem. Okay. All right. And then I move on, I fix that, and I move on to step 18. Oh, I got a problem here. Right. And now I need to address that problem. But if I've got variation in terms of initially just how the process is done, and then I try to understand the delta, what delta am I looking at to what standard?
We need a reference point at that point of time. A reference point.
Yeah, exactly. It's a line in the sand.
From the reference point, you start looking at the abnormality and go ahead. So this stabilizing, as you said, repeatability is, I think, the best that's what Sensei Masaki told me. When I saw the video and somebody questioned it, I said, that's probably the way he expressed it. But all I know what he said is that easy being able to repeat it the same way may not be the best way. At that point of time, that is the stabilizing that I understand. That's what I was taught, and you're just reinforcing.
No, you're correct, and you got to remember, Imai, Iwata, Nakao, they all came out of the same playbook, right? And the word stabilize is a language issue, I think, because people think stabilize means I have to take all the waste and abnormalities out of my process. Okay, and that's not what Imai means.
Is repeatability, and you have a frame of reference at that point of time.
You have a standard procedure, a repeatable procedure to do what you need to do to get the part built, right? And that's what he means by stabilization. So
thank you very much for this first part. Meet you again for the second part.